Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to settle in wherever you are. Let your body sink into comfort, releasing whatever tensions the day has left behind. There's nowhere you need to be, nothing you need to accomplish. Just gentle exploration ahead. Where in the world are you right now? A quiet room where you can finally let your mind rest. A peaceful space where the day's noise has faded. Wherever you are, you're exactly where you need to be. Tonight we're going to explore one of physics' most profound mysteries, singularities, the points where the universe breaks down, where our equations produce infinities, where space and time cease to make sense. We'll discover that singularities hide at the hearts of black holes, mark the beginning of the universe, and represent boundaries where our understanding fails. These are not just mathematical curiosities, but places where reality itself becomes undefined. But don't worry, this isn't going to be an overwhelming journey through impenetrable mathematics or a dizzying plunge into conceptual impossibilities. Instead, we'll move slowly and thoughtfully through these breakdown points, building understanding piece by piece, finding clarity where confusion seemed inevitable. By the end, I think you'll have a richer appreciation not just for what singularities are, but for what they reveal about the limits of physics and the nature of reality. If you enjoy these calm explorations of cosmic extremes and physical boundaries, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being part of this community of curious minds, so settle in now. Let your shoulders drop, releasing tension you didn't know you were carrying. Take a slow, deep breath in, feeling your lungs expand, and release it gently. Feel yourself sinking deeper into comfort with each exhale. And let's begin our slow drift through the places where physics breaks, exploring singularities where density becomes infinite, where time stops, where our theories fail and reality becomes undefined. There's nowhere you need to be, no boundaries you must cross. Just listen, and let the mysteries of breakdown points unfold like space-time itself curving to infinity. To understand singularities, we must first define what we mean when we say that physics breaks down, that the universe reaches a point where it stops making sense. In physics and mathematics, a singularity is a point where a function or equation becomes undefined, where values approach infinity or lose mathematical meaning. The simplest example is dividing by zero. In ordinary arithmetic, 1 divided by 0 is undefined. As the denominator approaches 0, the result approaches infinity. This mathematical singularity is innocuous, a quirk of arithmetic. But when singularities appear in physical theories, they signal something profound. They mark boundaries where our descriptions of reality fail, where the equations we use to understand nature produce nonsensical results. In general relativity, Einstein's theory of gravity and space-time, singularities are points where space-time curvature becomes infinite. At these points, density becomes infinite, temperature becomes infinite, the gravitational field becomes infinite. These infinities are problems. Physics doesn't like infinities appearing in physical quantities. They usually indicate the theory has been pushed beyond its valid domain. When a theory predicts infinities, it's telling us it's incomplete, that something is missing from our understanding. General relativity predicts singularities in two main contexts. At the centres of black holes and at the beginning of the universe in the Big Bang. These aren't abstract mathematical artifacts, but genuine physical situations our universe contains or has experienced. At a black hole's centre, all the mass that created the black hole is compressed to infinite density in a single point. Or more accurately, general relativity says it should be compressed to infinite density. But this is almost certainly wrong. Different approaches to quantum gravity suggest different resolutions. String theory, loop quantum gravity, and other frameworks each propose mechanisms, but without complete quantum gravity theory. We can't definitively say what happens at singularities. What we can say is that singularities mark limits of our knowledge, boundaries between understood and unknown. They're not failures of reality, but failures of our theories. Reality continues at singularities, but our description fails. This is important distinction. Singularities aren't places where universe literally breaks, but places where our physics breaks. The universe knows what it's doing. Our theories don't yet capture it completely. Singularities thus serve dual purpose. They're predictions of general relativity, showing where extreme gravity leads, and they're signposts indicating where new physics is needed, where general relativity must be supplemented or replaced. In this sense, singularities are gifts to physics. They clearly mark frontiers where discoveries await. Rather than being embarrassing failures, they're opportunities. They tell us where to focus efforts to develop better theories. Throughout this exploration, we'll examine different types of singularities, what they mean physically, and what they reveal about reality's nature. We'll see that singularities connect to deepest questions: the universe's origin, black holes' interiors, time's nature, and quantum gravity. Understanding singularities means understanding boundaries of knowledge and glimpsing what lies beyond current theories. The most famous singularity is the one that began the universe, the Big Bang Singularity at time zero, where everything emerged from infinite density. In standard Big Bang cosmology, if we trace the universe's expansion backward in time, we reach a moment when everything was compressed together. As we go further back, density and temperature increase without bound. Eventually we reach a point of infinite density at finite time in the past. This is the Big Bang Singularity. General relativity predicts that the universe emerged from this singular point 13.8 billion years ago. At the singularity, the entire observable universe, everything we can see, was compressed to zero volume. Not just very small, mathematically zero. All the matter and energy in infinite density at a single point. Temperature was infinite, space-time curvature was infinite, physical conditions were as extreme as conceivable, or rather, inconceivable. These infinities are physically meaningless. They indicate the theory's breakdown. The Big Bang Singularity is thus both foundation of cosmology and sign of cosmology's incompleteness. It marks the beginning of time in standard model. Before the singularity, time doesn't exist in this framework. Asking what happened before the Big Bang is like asking what's north of the North Pole. The question presumes structure that doesn't exist. If time began at the singularity, there is no before. The concept of before requires time to make sense. This resolves certain philosophical questions about causation. The universe needs no cause if time began with it, but it creates others. Why did the universe begin? What determined initial conditions? Why a singularity at all? These questions motivated cosmologists to look for ways to resolve or avoid the Big Bang singularity. Inflation. The theory of exponential expansion in the early universe pushes observable universe's origin back, but doesn't eliminate the singularity. Inflation describes what happened after the singularity, smoothing and expanding space. But it doesn't explain the singularity itself. To address the singularity requires quantum gravity. At Planck Scale energies and densities, quantum effects dominate. Classical general relativity breaks down. Quantum mechanics must be incorporated into gravitational description. Various quantum cosmology approaches attempt this. The Hartley-Hawking no-boundary proposal suggests the universe has no initial singularity. In their model, time becomes space-like near the Big Bang. There's no sharp beginning, just smooth geometry. This is achieved using imaginary time, mathematical technique from quantum mechanics. The singularity is smoothed out. Loop quantum cosmology, based on loop quantum gravity, predicts a quote zero instead of Big Bang singularity. Quantum effects create repulsive pressure at extreme densities. The universe contracts to minimum size, then bounces into expansion. The singularity is replaced by a bounce. The universe emerged from a previous contracting phase rather than from nothing. Yet it also marks the boundary where our physics fails, where quantum gravity is needed. The singularity reminds us that even our most successful theories have limits. The fundamental questions about origins remain. Whether the Big Bang was truly a singularity, or something more subtle revealed by quantum gravity, is one of cosmology's deepest mysteries. Understanding what happened at time zero requires understanding quantum gravity, connecting cosmology's beginning to physics frontier. While the Big Bang singularity lies in the past, black hole singularities exist now, hidden within every black hole in the universe. When a massive star exhausts its nuclear fuel, it can no longer support itself against gravity. The core collapses catastrophically. If the core's mass exceeds about 3 solar masses, nothing can stop the collapse. Gravity overwhelms all other forces. The core collapses to infinite density, forming a singularity. This singularity is surrounded by an event horizon, creating a black hole. The event horizon is the boundary from which nothing, not even light, can escape. It's defined by the escape velocity reaching light speed. At the Schwarzschild radius for a given mass, escape velocity equals light speed. This radius defines the event horizon's location. For a solar mass black hole, the Schwarzschild radius is about 3 kilometers. For a billion solar mass black hole, it's 1 billion kilometers. Inside the event horizon, all paths lead inward toward the singularity. Space and time swap roles in a sense. Perhaps quantum effects prevent complete collapse, leaving a tiny but finite region of extreme density. Or perhaps the singularity is real, but space-time itself becomes quantum mechanical there, without classical geometry. String theory suggests singularities might be replaced by extended objects like strings or higher dimensional structures. Loop quantum gravity predicts quantum geometry might prevent singularities, replacing them with high-density regions. But without quantum gravity theory we can test. These remain educated speculations. The Penrose singularity theorem, proven by Roger Penrose in 1965, shows singularities are generic in general relativity. Under reasonable conditions, gravitational collapse inevitably produces singularities. They're not special cases but general predictions. This made physicists take singularities seriously as real features requiring explanation, not just mathematical artifacts. Stephen Hawking extended these results, proving that the Big Bang singularity is also generic under certain assumptions, together. The singularity theorem showed that general relativity predicts its own breakdown in extreme conditions. This is remarkable self-awareness for a theory. It clearly indicates where it's no longer valid. Black hole singularities are shielded from outside view by event horizons. This is cosmic censorship. Cosmic censorship conjecture suggests that singularities are always hidden behind horizons, never naked and visible. If true, this protects the external universe from singularities' pathological effects. We can never observe them directly. This is simultaneously reassuring and frustrating. Reassuring because singularities can't affect us. Frustrating because we can't observe them to test quantum gravity. Hawking's discovery that black holes radiate adds another wrinkle. Black holes aren't truly black but emit thermal radiation. Over enormously long timescales, black holes evaporate completely through Hawking radiation. What happens to the singularity during evaporation? Does it disappear with the event horizon? Or does it become naked at the end, violating cosmic censorship? These questions connect to the information paradox. If black holes evaporate, what happens to information that fell in? The singularity seems to destroy information, violating quantum mechanics' unitarity. This is a deep problem. Recent work suggests information might be preserved through subtle quantum correlations in Hawking radiation. But exactly what happens to the singularity during evaporation remains unclear. Black hole singularities thus raise fundamental questions about gravity, quantum mechanics, information, and reality's nature. They're not just exotic endpoints of stellar evolution, but laboratories for understanding physics at its most extreme. Understanding black hole singularities is key to understanding quantum gravity and resolving conflicts between general relativity and quantum mechanics. Not all singularities are the same. Different solutions to Einstein's equations produce different types of singularities with distinct properties. The Schwarzschild singularity describes a non-rotating, uncharged black hole. It's the simplest black hole solution. In Schwarzschild coordinates, the singularity appears as a point at the centre with infinite curvature. But this is coordinate-dependent description. The singularity's nature is more subtle. The Schwarzschild singularity is a moment in time, not a place in space, from the perspective of infalling matter. Once inside the event horizon, the singularity lies in the future, inevitable as tomorrow. The Kerr singularity describes rotating black holes, which are more realistic since most stars rotate. Rotation changes the singularity structure dramatically. Instead of a point, it becomes a ring singularity. The ring lies in the black hole's equatorial plane. It has zero thickness but finite radius. Time-like singularities are encountered by time-like observers in finite proper time, like black hole interiors. Space-like singularities extend across space at a given time, like the Big Bang. Null singularities would be encountered by light rays, lying on null surfaces. Curvature singularities involve infinite space-time curvature and are generally considered physically significant. Coordinate singularities are artifacts of particular coordinate choices and can be removed by coordinate transformations. The event horizon in Schwarzschild coordinates appears singular, but it's actually just a coordinate singularity. Switching to different coordinates like Kruskal-Szekeres shows the horizon is smooth, not singular. True singularities persist in all coordinate systems. They're genuine features of space-time geometry. Distinguishing real singularities from coordinate artifacts requires careful mathematical analysis. Curvature invariants, quantities that don't depend on coordinate choice, reveal true singularities by becoming infinite. The distinctions between singularity types matter for understanding their physical implications and possible resolutions. Different types might require different quantum gravity treatments or have different observational consequences. Some might be resolved by quantum effects, while others might be more fundamental. Understanding singularity taxonomy helps organize our ignorance and guide theoretical development. It shows that singularity isn't a monolithic concept, but encompasses various breakdown modes of general relativity. Each type tells us something about how gravity behaves in extreme conditions, and where quantum effects become essential. The cosmic censorship hypothesis attempts to protect the universe from singularity's pathological effects by ensuring they remain hidden. Roger Penrose proposed cosmic censorship in 1969 after singularity theorem showed that general relativity generically predicts singularities. If singularities form from realistic collapse but remain visible, they could wreak havoc on physics. At naked singularities, causality might break down. Predictability could fail. Physics as we know it might become impossible. Cosmic censorship suggests nature prevents this. Singularities from gravitational collapse are always hidden behind event horizons. The weak cosmic censorship conjecture states that singularities forming from generic gravitational collapse are invisible from infinity. They're cloaked by event horizons, preventing outside observers from seeing them or being affected by their pathology. This protects the external universe. We can't probe singularities directly, but we're also not threatened by them. The strong cosmic censorship conjecture is more stringent. It states that singularities are invisible to all observers, not just distant ones. Even observers inside black holes shouldn't encounter naked singularities in generic situations. Strong cosmic censorship ensures that space-time is globally well behaved, with predictability preserved everywhere possible. These conjectures remain unproven despite decades of effort. They're believed likely true but not proven rigorously. Counterexamples exist in idealized scenarios with perfect symmetry or special initial conditions, but these might be unstable. Small perturbations could restore censorship, clothing any would-be naked singularities. Numerical simulations generally support censorship. Realistic collapse scenarios seem to produce clothed singularities, but simulations have limitations. They can't capture all possibilities or run to infinite precision. Hawking radiation complicates the picture. As black holes evaporate, event horizons shrink. Eventually the horizon might disappear entirely, potentially exposing the singularity. This would violate cosmic censorship at the end of black holes' life. Whether this actually happens depends on poorly understood quantum gravity effects during final evaporation stages. Some scenarios suggest a remnant remains, preserving the singularity behind residual horizon. Others propose the singularity dissolves before the horizon disappears, resolving both simultaneously through quantum effects. Without understanding quantum gravity, we can't definitively predict final evaporation's outcome. Cosmic censorship is important not just as hypothesis, but as guide for theoretical development. It suggests which solutions to Einstein's equations are physically realistic versus mathematical curiosities. It constrains possible forms of matter and energy, since some might violate censorship. Testing cosmic censorship requires understanding both classical collapse and quantum gravity. Observations of black holes provide indirect tests. So far, all observed black holes have horizons, as censorship requires. Gravitational wave observations from merging black holes show behavior consistent with horizons, supporting censorship. Whether nature truly respects this boundary, protecting us from singularity's full strangeness, remains open question. The answer will likely emerge from quantum gravity, revealing whether singularities are truly hidden, resolved, or perhaps more benign than classical theory suggests. To understand singularities, we must consider what happens if you fall into a black hole, experiencing the journey to the singularity firsthand. From safe distance, a black hole appears as dark sphere, the event horizon surrounded by accretion disk or space. As you approach, gravitational pull strengthens, the escape velocity increases approaching light speed. At the event horizon itself, escape velocity equals light speed. This marks the point of no return. Crossing the event horizon is called passing through, though quote 2 is more accurate since you're accelerating inward. From your perspective, falling freely, crossing the horizon seems unremarkable. No physical barrier or wall exists there. You wouldn't notice anything special at the moment of crossing. The horizon is not a physical surface but a mathematical boundary. But something profound has changed. You're now causally disconnected from the external universe. No signal you send can escape to reach outside. The horizon is one-way membrane for causation. From outside observers' perspective, events look different. They never see you cross the horizon. Gravitational time dilation becomes infinite at the horizon from external viewpoint. As you approach, light from you becomes increasingly redshifted and time dilated. You appear to slow down, taking infinite time to reach the horizon. Your image freezes, fading to invisibility. But this is artifact of external perspective. In your proper time, you cross quickly and continue falling inward. Once inside, all paths lead toward the singularity. Space and time's roles exchange in important sense. Moving away from the singularity becomes impossible, like trying to move backward in time externally. The singularity lies in your future as inevitably as tomorrow. There's no escaping it. As you fall deeper, tidal forces grow stronger. These are gradients in gravitational field. Your feet are closer to the singularity than your head, so they feel stronger pull. This differential force stretches you along the radial direction, a process called spaghettification. For stellar mass black hole, tidal forces become lethal long before reaching the singularity. You'd be torn apart, then your atoms would be torn apart long before the final moment. But for supermassive black hole, tides at the horizon are weak. You could cross comfortably. A billion solar mass black hole has horizon radius of billion kilometers. Tidal forces there are negligible. You could survive well inside, observing the strange interior environment for some time. Eventually, though, as you approach the singularity, tidal forces grow without bound. No matter how large the black hole, the singularity eventually destroys anything approaching it. The final approach is dominated by infinite tidal forces. Space is stretched and compressed catastrophically. General relativity predicts that you reach the singularity in finite proper time after crossing the horizon. For Schwarzschild black hole, it takes microseconds to reach the singularity after crossing the horizon of stellar mass black hole. For supermassive black hole, it might take hours or days to reach the singularity after crossing. At the singularity itself, classical general relativity breaks down completely. Curvature becomes infinite. What actually happens to matter at the singularity is unknown. Does it cease to exist? Transform into something else? Quantum gravity must answer these questions. Classical theory cannot. The journey to the singularity is both a physical process and a probe of physics' limits. It represents ultimate extreme condition, where our theories must be pushed to their breaking point. Understanding this journey requires unifying general relativity and quantum mechanics, the holy grail of theoretical physics. The tidal forces near singularities are so extreme they tear apart anything that approaches, a process vividly called spaghettification. Tidal forces arise from gravity's gradient. Gravitational field strength changes with distance from the source. Your feet, being closer to Earth than your head, feel slightly stronger gravity. This differential is tidal force. On Earth, tidal forces are negligible for human body. The difference between head and feet is tiny, but near black hole singularity, gravitational gradients are extreme. Tidal forces become overwhelmingly strong. Consider falling feet first toward a black hole. Your feet are closer to the singularity, feeling stronger gravitational pull. The difference in gravitational force between your feet and head grows as you approach. This differential force stretches you along the direction toward the singularity, like taffy being pulled. Then tissues would tear, bones would crack. Eventually you'd be pulled into a stream of atoms. The atoms themselves would be torn apart eventually, electrons stripped from nuclei by tidal forces. Even nuclei might be disrupted at close enough proximity to the singularity. For supermassive black hole, the situation is different. The horizon radius is much larger. A billion solar mass black hole has a horizon of 1 billion kilometers, about 7 astronomical units. Gravitational gradient at such large radius is much gentler. Tidal forces at the horizon are tiny. You could cross the event horizon of supermassive black hole without noticing anything unusual. The stretching would be imperceptible. You'd remain intact, at least initially. This is because tidal force scales as mass divided by radius cubed. Larger black holes have weaker tidal forces at their horizons, but this is temporary reprieve. As you continue falling inward, approaching the singularity, tidal forces eventually become extreme. The singularity itself has zero size in classical theory. Gradients there become infinite. No structure can withstand infinite tidal forces. Everything is torn to fundamental constituents. Mathematically, tidal forces are described by Riemann curvature tensor components. Specific components measure stretching in different directions. At singularity, these diverge to infinity. The Weyl curvature, in particular, characterizes tidal effects. It becomes infinite at curvature singularities. Quantum effects might modify this picture. Perhaps tidal forces are limited by quantum gravity effects. If singularities are resolved into extended quantum objects, tidal forces might remain large but finite. Or perhaps quantum properties of matter change behavior when tidal forces approach Planck Scale. These possibilities remain speculative without quantum gravity theory. Observing spaghettification directly is impossible since it occurs inside event horizons. but tidal disruption events occur when stars pass too close to black holes outside the horizon. The star is stretched and torn apart by tidal forces, creating bright flare as material is accreted. These events are observed by telescopes, providing indirect evidence of extreme tidal forces near black holes. They show what would happen to you, but outside the horizon where light can still escape. Inside the horizon, spaghettification proceeds unseen, culminating in complete disruption at the singularity. This fate awaits anything falling into black hole. No structure, no matter how strong, can resist infinite tidal forces. Its ultimate destruction, total reduction to undefined state at the singularity. Understanding spaghettification helps appreciate singularity's physical extremity, and why new physics is needed to describe them. Inside a black hole's event horizon, time and space behave in profoundly strange ways that defy ordinary intuition. General relativity describes space-time as four-dimensional structure, with 3 space dimensions and 1 time dimension. Time dimension is distinguished from space by its signature in the metric. Time is different from space mathematically. Outside a black hole, time flows forward universally. You can move through space, but not through time arbitrarily. Inside the event horizon, when something remarkable happens, the time-like and space-like directions exchange roles in certain sense. The radial direction toward the singularity becomes time-like. Moving toward the singularity is like moving forward in time. You cannot avoid moving toward the singularity, just as outside you cannot avoid moving forward in time. The singularity doesn't lie at a place in space. It lies in the future, a moment in time you will inevitably reach. The exterior universe, if you could see it, would appear compressed into shrinking region behind you. Meanwhile, looking toward the singularity, you see your future, the moment of your destruction. Time dilation effects inside are complex. Different observers inside measure different proper times to the singularity depending on when they entered. But all proper times are finite. Everyone reaches the singularity eventually, regardless of their path. The Penrose diagram, a conformal mapping of space-time, visualizes these relationships elegantly. It shows how light cones tilt inside the horizon, directing all future trajectories toward the singularity. The diagram makes clear that the singularity is a space-like boundary, extending across space at the final moment. Everyone who enters the black hole hits the singularity at different spatial locations, but all at their local future endpoints. This is different from Big Bang Singularity, which is a space-like boundary in the past from which everything emerged. Black hole singularity is future boundary toward which everything falls. They're temporally opposite. The interior's strange geometry has consequences for causality and information. Once inside, you could in principle send signals to other infalling matter, but nothing can escape to the outside. The interior is causally disconnected from exterior. Events inside cannot influence events outside. This causal structure is part of what makes black holes so enigmatic. Information appears to vanish from universe. Rotating black holes have even stranger interiors. The Kerr solution predicts inner horizons and regions with closed time-like curves. These features are likely unphysical, destroyed by instabilities, but they show how rotation complicates interior geometry. Near the singularity, quantum effects must become important. Classical space-time description breaks down. Perhaps time itself becomes meaningless, or quantum mechanical near the singularity. The smooth classical picture of space-time flowing toward inevitable end might be replaced by quantum foam. Understanding what really happens requires quantum gravity, which would modify both spatial and temporal descriptions. Time and space inside black holes challenge our basic intuitions about reality's structure. They show that space-time is dynamical, with properties changing dramatically in extreme gravitational fields. The breakdown of ordinary space and time concepts near singularities is part of what makes them so fascinating and mysterious. Black hole singularities create a profound problem called the information paradox. challenging fundamental principles of quantum mechanics. In quantum mechanics, information cannot be destroyed. This is consequence of unitary evolution. Quantum states evolve deterministically according to Schrödinger equation. Initial states uniquely determine future states. Reverse is also true. Given a final state, you can in principle reconstruct the initial state. This means information is preserved. Whatever information existed initially continues to exist, though perhaps scrambled. Classical black holes seem to violate this principle. Matter falling into a black hole crosses the event horizon. The matter continues to the singularity, where general relativity says it's destroyed. From outside, all information about what fell in seems lost. The black hole is characterized only by mass, charge, and angular momentum. This is called the no-hair theorem. Black holes have no hair, meaning no other distinguishing features. Whether you throw in an encyclopedia or equivalent mass of random atoms, the resulting black hole is identical. All the detailed information in the encyclopedia seems to vanish, leaving only the black hole's total mass. This apparent information loss troubled physicists. It contradicts quantum mechanics' fundamental principles. Physicists have proposed various resolutions over decades. Each has strengths and challenges. One proposal is that information is encoded in Hawking radiation through subtle correlations. Though radiation appears thermal locally, there might be non-local correlations that encode information. Extracting the information requires waiting for entire evaporation and analysing all the radiation collectively. Another proposal involves black hole complementarity. Information is encoded both inside and outside simultaneously. Different observers see different aspects. Infalling observers see information cross the horizon. External observers see it encoded in radiation. This requires observers can't compare notes, which is true since infalling observers don't return. Recent developments involve the holographic principle and ADS/CFT correspondence. These suggest that black hole interior and exterior are dual descriptions of the same quantum information. Information isn't lost because interior and exterior aren't truly separate in the quantum description. The role of the singularity in these resolutions is unclear. Does it need to exist for information preservation? Or is singularity resolved by quantum effects, replaced by something that can return information? Some proposals suggest firewalls at the horizon, energetic surfaces that destroy information in a controlled way. But firewalls violate equivalence principle, which says horizons shouldn't be special for infalling observers. The debate continues. Recent calculations using path integrals and quantum extremal surfaces suggest progress. These techniques indicate that information does escape, with the quote 5 showing information return during evaporation. But exactly how information escapes and what happens at the singularity remains incompletely understood. The information paradox shows that singularities connect to quantum mechanics in deep ways. Resolving the paradox likely requires understanding quantum gravity and whether singularities truly exist quantum mechanically. It's not just academic puzzle, but crucial test of our understanding of quantum mechanics and gravity. The answer will reveal fundamental truths about information, quantum mechanics, gravity, and reality's ultimate structure. Hawking radiation fundamentally changes our understanding of black holes and raises questions about singularity's ultimate fate. In 1974, Stephen Hawking discovered that black holes aren't completely black, but emit thermal radiation. This was revolutionary. Classical black holes are perfect absorbers, capturing everything, emitting nothing. But quantum mechanics changes the picture. Vacuum isn't truly empty, but filled with quantum fluctuations. Virtual particle-antiparticle pairs constantly form and annihilate throughout space due to quantum uncertainty. Near a black hole's event horizon, something remarkable happens to these virtual pairs. Sometimes one particle falls into the black hole while its partner escapes to infinity. The escaped particle becomes real radiation. The partner that fell in has negative energy relative to infinity. Evaporation accelerates as the black hole becomes smaller and hotter. The process runs away. Eventually, the black hole evaporates completely in final explosion, releasing remaining energy as radiation. For stellar mass black hole, complete evaporation takes about 10 to the 67 years. For supermassive black hole with billion solar masses, it takes 10 to the 98 years. These timescales dwarf the current age of the universe by incomprehensible factors. But given infinite time, all black holes eventually evaporate, leaving no trace except diffuse radiation. This raises a profound question. What happens to the singularity during evaporation? As the black hole shrinks, the event horizon contracts. Eventually it might disappear entirely. Does the singularity become naked at the end, violating cosmic censorship? Or does the singularity disappear before the horizon, resolved by quantum effects? Or does a tiny remnant remain, preserving the singularity behind a minimal horizon forever? These questions cannot be answered with current understanding. The final stages require quantum gravity. As the black hole approaches Planck mass, about 10 to the -8 kilograms, quantum gravity becomes essential. Classical general relativity breaks down. The black hole becomes a quantum object requiring full quantum gravity treatment. What emerges from this quantum regime is unknown. It might be a burst of Planck Scale particles, or a stable Planck Scale remnant that persists indefinitely, or something entirely unexpected. The fate of the singularity is tied to information paradox. If information is preserved, singularity might need to be resolved. Hawking radiation also affects black hole interiors. Back reaction from radiation might modify interior geometry. Some calculations suggest the interior becomes dynamic, possibly affecting the singularity. Observing Hawking radiation directly is currently impossible. It's far too weak for existing technology. Primordial black holes, if they exist with small masses, might be detectable through their evaporation. A black hole with initial mass of about 10 to the 12th kilograms would be evaporating now. Such black holes would produce gamma-ray bursts. Searchers have found no convincing candidates. This constrains the abundance of primordial black holes in certain mass ranges. Hawking radiation is supported by theoretical consistency, analog experiments in condensed matter systems, and quantum field theory in curved spacetime. It's widely accepted despite no direct observation. The discovery showed that black holes are thermodynamic objects with temperature and entropy. This leads to black hole thermodynamics, with laws analogous to classical thermodynamics. The entropy is proportional to horizon area, not volume. This is the Bekenstein-Hawking entropy. This holographic scaling suggests that information in a region is encoded on its boundary, not throughout its volume. These insights connect black holes to quantum information theory, thermodynamics, and holography. Hawking radiation transformed black holes from purely gravitational objects to quantum phenomena. It connects gravity, quantum mechanics, and thermodynamics in ways still being explored. Understanding Hawking radiation and evaporation fully requires understanding quantum gravity and singularity resolution. The black hole's ultimate fate, and the singularities, remains one of physics' deepest mysteries. Singularities demand quantum gravity because they're where both quantum mechanics and gravity become equally important, each indispensable. General relativity is classical theory. It treats space-time as smooth continuum described by deterministic equations. Quantum mechanics governs microscopic world. It introduces uncertainty, superposition, and probabilistic behavior. These theories are incompatible in fundamental ways. They make different assumptions about reality's nature. General relativity is deterministic and continuous. Quantum mechanics is probabilistic and discrete. At ordinary scales, we can use each theory in its own domain without conflict. A unified theory, quantum gravity, is needed to describe physics where both effects are crucial. Quantum gravity should resolve singularities, replacing infinities with finite quantum descriptions. It should tell us what happens at black hole centers and at the Big Bang, where classical theory fails. Developing quantum gravity is extraordinarily difficult. Gravity resists straightforward quantization. Attempts to quantize general relativity directly produce non-renormalizable theories with infinities that can't be removed. Standard quantum field theory techniques, successful for other forces, fail for gravity. This technical difficulty motivates alternative approaches, string theory, loop quantum gravity, and others. String theory proposes fundamental entities are one-dimensional strings, not point particles. Extended nature of strings softens ultraviolet behavior, potentially avoiding gravitational infinities. String theory predicts extra spatial dimensions and requires supersymmetry for consistency. It unifies gravity with other forces naturally, potentially providing complete quantum theory of everything. Loop quantum gravity takes different approach. It quantizes space-time geometry directly. Space becomes discrete at Planck Scale, built from fundamental quantum loops. This discreteness prevents singularities, replacing them with quantum bounces or tunneling events. Loop quantum gravity doesn't assume extra dimensions or supersymmetry, but focuses purely on quantizing general relativity. Other approaches exist: causal dynamical triangulations, asymptotic safety, emergent gravity. Each has strengths and weaknesses. None is experimentally confirmed yet. The Planck scale marks where quantum gravity becomes essential. At this scale, quantum fluctuations of geometry become significant. Planck length is about 10 to the minus 35 meters. Planck time is about 10 to the minus 43 seconds. Below these scales, spacetime might not exist as smooth continuum, but become quantum foam. Singularities occur in this quantum gravity regime. Classical description breaks down. Quantum gravity should provide resolution, explaining what replaces the singular classical geometry. Observations can't directly probe Planck scale. Energies required are far beyond any foreseeable experiment. But cosmology and black holes provide indirect tests. Signatures might appear in cosmic microwave background or gravitational waves. Precise measurements might reveal quantum gravity effects, discriminating between theories. Until then, theoretical consistency and mathematical beauty guide development. Singularities serve as theoretical laboratories, places where quantum gravity must operate. Understanding singularities requires quantum gravity. Understanding quantum gravity requires studying singularities. They're deeply intertwined, each informing the other. Resolving singularities is major motivation for quantum gravity research. When we finally understand quantum gravity, singularities will likely be explained or eliminated. They'll transform from places where physics breaks to places where new physics operates. This transformation from infinities to finite quantum descriptions is what quantum gravity promises. String theory offers one approach to resolving singularities by replacing point particles with extended objects that smooth out gravitational infinities. In string theory, fundamental constituents aren't zero-dimensional points, but one-dimensional strings. These strings are extraordinarily small, about Planck length in size, far below any observable scale. They can be open with endpoints or closed loops. Different vibration modes correspond to different particles. One particular vibration mode corresponds to the graviton, the hypothetical quantum of gravity. This automatically incorporates gravity into quantum framework. String theory is inherently a quantum theory of gravity. The extended nature of strings resolves certain infinities that plague point particle theories. When point particles interact at a single spacetime point, calculations can produce infinite results. These excited states have finite size. They resist further compression, preventing infinite density. The singularity is replaced by a region of extreme but finite string density and curvature. Similarly, The Big Bang Singularity might be a transition between different phases or dimensions. In pre-Big Bang scenarios from string theory, the universe might have existed before in different form. The Big Bang becomes a transition rather than absolute beginning, or the universe might emerge from collision of higher dimensional branes, creating Big Bang in each brane. String theory also predicts duality symmetries connecting different descriptions. Some singularities in one description become smooth in dual description. This suggests certain singularities are artifacts of particular perspectives, not physical realities. Black holes in string theory are described by bound states of branes and strings. The entropy counting from these microscopic states reproduces Bekenstein-Hawking entropy. This is major success, explaining black hole entropy from fundamental degrees of freedom. It suggests black holes aren't singular, but have rich microstructure of strings and branes. The information paradox might be resolved through this microstructure. Information is stored in string configurations. As black hole evaporates, information returns through subtle correlations in Hawking radiation. String theory provides framework where this can be calculated explicitly in certain cases. However, string theory faces challenges. It's not yet fully formulated non-perturbatively. Many calculations work only in specific limits or with simplifying assumptions. The vast landscape of compactifications makes unique predictions difficult, and experimentally testing string theory is enormously challenging. Direct tests require Planck Scale energies. Indirect tests through cosmology or black holes might eventually provide evidence. For now, string theory remains promising framework but unconfirmed theory. Its treatment of singularities is sophisticated but not yet definitive. Whether string theory correctly describes quantum gravity and resolves singularities remains open question, but it demonstrates that singularities can potentially be resolved in consistent quantum gravity theory. It shows that infinities of classical theory might disappear when quantum and gravitational effects are properly unified. Loop quantum gravity takes a different approach to singularities, directly quantizing space-time geometry and predicting that singularities are replaced by quantum bounces. Loop quantum gravity, or LQG, doesn't add extra dimensions or new particles. It quantizes general relativity itself. The approach treats space-time geometry as quantum mechanical variable from the start. Space is described by a network of quantum loops called spin networks. This minimum volume prevents singularities. Density cannot become infinite because volume cannot become zero. As matter collapses toward what would classically be a singularity, quantum effects become strong. These quantum effects create repulsive pressure that halts and reverses the collapse. Instead of reaching infinite density, the system bounces at very high but finite density. This applies to both black hole interiors and cosmological singularities. In loop quantum cosmology, application to early universe, the Big Bang becomes a big bounce. The universe contracted from a previous phase, reached minimum size, then bounced into the expansion we observe. The bounce occurs at density around 1/10 of Planck density, still enormous but finite. This resolves the Big Bang singularity without invoking extra dimensions or exotic matter. For black holes, loop quantum gravity predicts the interior singularity is replaced by transition region. Matter collapses to extreme density, bounces, and potentially emerges in another region of space-time. This might create white holes, hypothetical objects that expel rather than absorb matter. Or it might create baby universes, new expanding regions connected through Planck Scale throats. These scenarios remain speculative. The mathematics is difficult, and full quantum description of black hole interiors isn't complete. But the basic picture is clear. Singularities are replaced by quantum transitions at Planck scale. Loop quantum gravity makes specific predictions. Gravity becomes repulsive at very high densities. The bounce scenario predicts modifications to early universe cosmology potentially observable in cosmic microwave background. So far, observations are consistent with standard inflation. but haven't definitively ruled out loop quantum cosmology modifications. Black hole signatures from loop quantum gravity might appear in Hawking radiation spectrum. Deviations from pure thermal spectrum could indicate quantum geometry effects. These predictions remain difficult to test with current technology. Loop quantum gravity faces its own challenges. Recovering full classical general relativity from quantum theory is technically difficult. The relationship between loop quantum gravity and particle physics isn't yet clear, and many calculations can be performed only in simplified models, not full theory. Despite challenges, loop quantum gravity provides concrete framework for singularity resolution. It shows that quantizing geometry naturally prevents infinities through fundamental discreteness. The predictions are testable in principle, connecting quantum gravity to observable cosmology. Whether loop quantum gravity is correct description of quantum spacetime remains to be determined, but it demonstrates that singularities need not be inevitable in quantum gravity. They can be replaced by bounces or transitions, resolving classical theory's breakdown through quantum effects. This gives hope that singularities are artifacts of classical approximation, not features of fundamental reality. The Planck Scale represents the fundamental limit where quantum gravity becomes essential, the scale where singularities resolution must occur. Max Planck discovered these fundamental scales in 1900 by combining fundamental constants: speed of light, gravitational constant, and Planck's constant. These combinations yield natural units: Planck length, Planck time, Planck mass, Planck energy, and others. Planck length is about 10 to the minus 35 meters, 20 orders of magnitude smaller than a proton. Planck time is about 10 to the minus 43 seconds. Time light takes to cross 1 Planck length. This prevents probing subplanck distances with any measurement. Planck length is fundamental limit. At Planck time, causality and temporal ordering might break down through quantum fluctuations. Space-time might not exist as smooth continuum at Planck scale, but become quantum foam. This foam is seething quantum activity, virtual black holes forming and evaporating, geometry fluctuating wildly. Classical concepts like distance and duration lose meaning in this regime. Singularities occur at or near Planck scale. At black hole center, conditions reach Planck densities. At Big Bang, Planck scale was reached at about 10 to the minus 43 seconds. Before this moment, classical Big Bang cosmology is invalid. Quantum gravity is needed. The Planck scale is thus the boundary where classical physics fails and quantum gravity begins. Understanding what happens at Planck scale is understanding what replaces singularities. No experiments can directly reach Planck energies. Building collider energetic enough is impossible. Required energy concentration would create black holes before accelerating individual particles to Planck energy. So Planck scale physics must be studied indirectly through astrophysics and cosmology. Black holes and early universe are natural laboratories where Planck scale physics operated. Signatures might remain in observable phenomena: cosmic microwave background, gravitational waves, black hole evaporation. Precise measurements might detect tiny deviations from classical predictions, fingerprints of quantum gravity. This is difficult because effects are suppressed by enormous factors, ratios of Planck scale to observable scales. But it's possible in principle. This motivates precision cosmology and gravitational wave astronomy. The Planck scale also has philosophical significance. It might represent fundamental graininess of space-time. If space and time are discrete at Planck scale, they're not infinitely divisible continua. This would resolve Zeno's paradoxes and answer ancient questions about space and time's nature. Or perhaps Planck scale marks transition to different regime where space-time is emergent phenomenon. Below Planck scale, more fundamental description might not involve space and time at all. These speculations venture beyond established physics. But Planck scale invites such thinking. It's the boundary between known and unknown, where our theories admit their incompleteness. Singularities bring us to this boundary. They're Planck Scale phenomena requiring Planck Scale physics. Understanding singularities means understanding Planck Scale. Understanding Planck Scale means developing quantum gravity. The two are inextricably linked. Singularities are windows into Planck Scale physics. When quantum gravity is understood, Planck Scale will be explained and singularities will be resolved. Until then, the Planck Scale remains a mysterious frontier. The scale where universe breaks and new physics must emerge. Given quantum gravity approaches suggest singularities might be resolved, we must ask, do singularities really exist, or are they illusions of classical theory? In classical general relativity, singularities are inevitable under reasonable conditions. The singularity theorems prove this. But classical general relativity is approximation. It's valid when quantum effects are negligible. At Planck scale, quantum effects are not negligible. Classical theory breaks down. The singularities predicted by classical theory might not survive inclusion of quantum effects. This is analogous to other situations in physics, where classical predictions are modified quantum mechanically. Classical electromagnetism predicts electrons should radiate away all energy and spiral into nucleus. Quantum mechanics prevents this through quantization of energy levels. Atoms are stable quantum mechanically. Similarly, classical collapse to singularity might be prevented by quantum effects. Perhaps quantum uncertainty principle prevents infinite compression. Perhaps quantum repulsion emerges. Perhaps singularities are replaced by high-density quantum states without true infinities. However, we cannot be certain without complete quantum gravity theory. It's possible that some form of singularity persists even quantum mechanically. Perhaps quantum singularities exist, points where quantum state becomes undefined or non-unique. These wouldn't be classical infinities but quantum analogues with their own pathology. Or perhaps singularities exist but are fundamentally quantum objects with no classical description. They might be regions where space-time doesn't exist, replaced by something more fundamental. Another possibility is that resolution depends on singularity type. Maybe space-like singularities like Big Bang are resolved, while time-like singularities in black holes persist. Or maybe naked singularities are impossible, but hidden singularities behind horizons are real. The existence question also depends on what we mean by, quote, 6. Do singularities exist if they're always hidden behind event horizons, causally disconnected from external universe? Even if they're real, they can't affect us directly. In practical sense, they might as well not exist for external observers. But for infalling observers, the question is urgent. Do you truly encounter singularity, or does quantum gravity save you? Current understanding suggests that classical singularities don't exist literally, but something extreme occurs at their locations. Whether that something qualifies as, quote, 7 is partly semantic. What's clear is that extreme physics operates where classical theory predicts singularities. Whether infinities exist or are replaced by finite quantum extremes, these regions are special. They're boundaries of space-time, edges where normal physical laws transition to quantum gravity regime. Resolving whether singularities truly exist requires experimental input from quantum gravity phenomena. Until observations can test Planck scale physics, we rely on theoretical consistency and mathematical beauty. Most physicists expect singularities are resolved by quantum effects. But certainty requires evidence. The question of singularity's existence is thus both physical and epistemological. It asks about nature's fundamental structure and about limits of our knowledge. Do mathematical features of our theories correspond to physical reality, or are they artifacts of approximation? The answer will come from quantum gravity, revealing whether universe truly breaks at singularities or simply transitions to unfamiliar physics. Singularities connect deeply to time's arrow, the mysterious directionality of time from past to future that defines our experience. The second law of thermodynamics states entropy always increases. This gives time its arrow, distinguishing past from future. But microscopic physical laws are time reversible. Run them backward and they still work. The arrow of time emerges from statistical mechanics and special initial conditions. The Big Bang Singularity provides these special initial conditions. The universe began in extremely low entropy state. This seems paradoxical. How can singularity, a point of infinite density and temperature, have low entropy? The resolution involves gravitational entropy. For gravity, uniform distribution has low entropy. Clumped matter has higher gravitational entropy. This is opposite of ordinary entropy. The early universe was very smooth and uniform. Gravitationally, this is low entropy. As structures formed, matter clumped. Gravitational entropy increased, consistent with second law. The Big Bang Singularity thus set initial conditions with low gravitational entropy. Everything since has been increased toward higher entropy, creating time's arrow. Without the special Big Bang initial conditions, there would be no thermodynamic arrow. The singularity is not just the beginning, but the source of temporal asymmetry. Black hole singularities relate differently to time's arrow. They're entropy reservoirs. Black holes have enormous entropy proportional to horizon area. Matter falling in increases black hole entropy while decreasing external entropy. Net entropy increases, but entropy is concentrated in black holes. Eventually, when black holes evaporate, entropy returns to thermal radiation. This process is irreversible. You can't uncollapse a black hole to recover original matter. The singularity destroys information about past states, making time's arrow stronger, or if information is preserved, it's scrambled so thoroughly that practical irreversibility results. Singularities thus both create and enforce time's arrow. The Big Bang Singularity set low entropy initial condition. Black hole singularities increase entropy irreversibly. These possibilities affect not just singularities, but our entire conception of time. Time might be an emergent phenomenon, arising from more fundamental timeless description. If so, singularities mark transitions between timeless quantum regime and classical temporal regime. They're boundaries where time emerges or dissolves, connecting temporal and timeless descriptions. The arrow of time might also be connected to cosmic expansion. Expansion provides cosmic time, a universal notion of simultaneity defined by expansion itself. Singularities mark beginning and possibly end of expansion, defining temporal boundaries. Understanding time's arrow requires understanding universe's thermal history from Big Bang to heat death. Singularities bookend this history, providing initial and final boundary conditions. They're not just points where physics breaks, but anchors defining temporal structure of entire universe. Singularities challenge determinism, the idea that present state completely determines future, one of physics' foundational principles. In classical physics, given complete information about current state, future evolution is uniquely determined by physical laws. Newton's laws are deterministic. Given positions and velocities now, you can calculate them at any future time. General relativity is also deterministic. Given space-time geometry on some slice, Einstein's equations determine evolution, but singularities disrupt this. They're places where determinism breaks down. At the Big Bang Singularity, there's no prior state from which to evolve. Initial conditions must be specified separately. This is problematic for determinism. Where do initial conditions come from if not from prior evolution? Quantum cosmology attempts to address this by proposing wave function of universe that doesn't require initial conditions. But this introduces quantum indeterminacy, trading one problem for another. Black hole singularities create different problem. What happens to information that reaches the singularity? If information is destroyed, then final state doesn't uniquely determine past state. Determinism is violated backward in time. This violates unitarity in quantum mechanics, which requires evolution to be reversible in principle. The information paradox is thus crisis for determinism. Proposed resolutions generally restore determinism by preserving information somehow. Either information is encoded in Hawking radiation, or interior and exterior are dual, or remnants persist. All these maintain deterministic evolution overall, though perhaps in subtle ways. Naked singularities, if they exist, would be a more serious problem. Without event horizon protecting external universe, singularity could causally affect outside regions. But since past near singularity is undefined, future evolution from singularity is unpredictable. This would create fundamental indeterminism in universe, regions where physics cannot predict outcomes. Cosmic censorship hypothesis prevents this by ensuring singularities are always hidden. If censorship holds, determinism is protected. Singularities can't inject unpredictability into accessible regions, but if censorship fails, determinism fails, the universe becomes fundamentally unpredictable. Quantum mechanics already introduces indeterminacy through measurement and wave function collapse. But this is different from classical determinism failure. Quantum probabilities are themselves determined by wave function evolution. Singularities threaten even this probabilistic determinism. If evolution cannot be defined through singularity, probabilities become meaningless. Understanding whether singularities preserve or violate determinism requires quantum gravity. If singularities are resolved, determinism might be restored. Quantum transitions replace undefined evolution. The bounce-in-loop quantum cosmology, for instance, provides deterministic connection between contracting and expanding phases. Information passes through bounce. Evolution is continuous even if classical description fails at bounce point. Similarly, if black hole singularities are replaced by quantum objects with well-defined evolution, determinism is maintained. The question connects to broader issues about causation and physical law. Can laws exist that don't determine outcomes uniquely? Or is determinism essential to concept of physical law? Some philosophers argue indeterminism is acceptable, even desirable. It allows for genuine novelty and freedom. Others maintain determinism is foundational. Without it, science cannot make predictions or explain phenomena. Singularities force us to confront these questions at the most fundamental level. They're where determinism is most threatened, and where preserving it requires new physics. Whether quantum gravity maintains determinism or requires accepting fundamental unpredictability is open question. The answer will shape our understanding of causation, physical law, and reality structure. Singularities might connect to the multiverse, particularly if they serve as portals between different universes or regions of reality. In eternal inflation, universe undergoes exponential expansion driven by inflation field. This expansion is eternal into future. Inflation ends locally in bubbles but globally continues forever. Each bubble becomes separate universe. Together they constitute the multiverse. The boundaries between bubbles are where inflation ends. These might be considered soft singularities. They're transitions between different phases rather than points of infinite curvature, but they mark breakdown of single smooth space-time into distinct causal regions. Some cosmological scenarios involve singularities connecting different universes more directly. In bouncing cosmologies, the bounce might connect our expanding phase to previous contracting universe. The big bounce replaces Big Bang Singularity, but also connects us to what came before. This previous universe might have different properties, different laws, or different dimensions. The bounce is boundary between universes, mediated by quantum gravity. Black hole singularities might also connect to other regions. Some solutions to Einstein's equations, like Kerr rotating black holes, contain inner horizons and possible passageways. Through the singularity, you might emerge in a different region of space-time or entirely different universe. These solutions are likely unphysical. Instabilities probably destroy inner structure, but they illustrate possibility that singularities could be portals rather than endpoints. In loop quantum gravity, black hole singularity might be replaced by transition to white hole. Matter falls in, bounces at Planck scale, and emerges as white hole explosion. This connects black hole interior to external space, possibly in distant future or different location. Baby universe scenarios propose that black hole interiors become new expanding universes. The singularity is replaced by new Big Bang, creating offspring universe. From outside it remains a black hole, but inside a new universe expands. This is speculative but consistent with some quantum gravity ideas. If true, black holes would be birthing new universes constantly. Our universe might be interior of black hole in parent universe. This creates genealogy of universes, each generation creating next through black hole formation. String theory landscape with 10 to the 500th possible vacua suggests vast multiverse. Different regions might have different compactifications, different physics. Transitions between vacua might involve singularities as boundaries. These ideas are highly speculative. We have no direct evidence for multiverse connections through singularities, but theoretical possibilities exist within quantum gravity frameworks. If singularities do connect to multiverse, it changes their interpretation profoundly. They're not endings but transitions, not breakdowns but gateways. This would make singularities more comprehensible. They're boundaries between phases or regions rather than absolute limits. Testing these ideas is extraordinarily difficult. Other universes are by definition causally disconnected. Even if our universe emerged from black hole in parent universe, we can't observe that parent. Even if black holes create baby universes, we can't access them from outside. The ideas remain in realm of theoretical speculation, but they show that singularities might play a larger role in cosmic structure than simply being problem points. They might be essential features enabling multiverse structure, connections between different regions of reality. Understanding singularities might require understanding multiverse and vice versa. They're potentially deeply connected aspects of quantum gravitational reality. Singularities raise profound philosophical questions about existence, causation, and limits of scientific knowledge. The most fundamental question: why is there something rather than nothing? The Big Bang Singularity sharpens this question. If universe emerged from singularity, where did singularity come from? If time began at singularity, quote 9 is meaningless. There's no temporal cause. This might dissolve the question. If time began with universe, asking what came before is incoherent, but it's philosophically unsatisfying to many. It seems to avoid rather than answer the question. Quantum cosmology approaches like Hartley-Hawking suggest universe has no boundary, no initial moment. In imaginary time, there's smooth geometry without beginning. Universe simply is. This eliminates need for cause by eliminating beginning. But it requires accepting mathematical framework that seems abstract. The question of existence connects to contingency and necessity. Is universe's existence necessary or contingent? Must it exist, or could it have not existed? If necessary, existence requires no further explanation, but what makes it necessary? If contingent, existence requires explanation. What brought contingent universe into existence? Singularities sit at intersection of these questions. They mark existence's boundaries. Another philosophical issue involves reduction and emergence. Physics typically explains complex phenomena by reducing them to simpler constituents and laws, but at singularities this breaks down. There's no deeper level to appeal to. The singularity is irreducible feature, at least within classical theory. This suggests limits to reductionism. Not everything might be explainable by appealing to simpler components. Some features might be fundamental, requiring acceptance rather than explanation. Singularities also challenge the principle of sufficient reason, the idea that everything has explanation. If singularity marks absolute beginning, what explains it? Nothing prior exists to provide explanation. Either principle of sufficient reason fails, or explanation must be non-temporal, or question is malformed. Different philosophical traditions respond differently. Theistic approaches invoke God as necessary being who created universe, including its initial singularity. Naturalistic approaches either accept brute facts without further explanation or seek scientific understanding through quantum cosmology. The epistemological status of singularities is also puzzling. They're predicted by our best theories but defined by those theories' breakdown. Can we trust theory about phenomena where it admits failure? This is similar to using map to find the edge of the map. The tool describes its own limit. Singularities force us to think about scientific theories' limits and scope. They're predictions and boundaries simultaneously. Understanding this requires philosophical sophistication about scientific knowledge's nature. Singularities also connect to questions about laws of nature. Do physical laws exist independently, constraining possibilities? Or are they descriptions of regularities that happen to obtain? At singularities, laws break down. Does this mean laws don't exist fundamentally? Or does it mean we've discovered laws' domain of validity, beyond which different laws apply? These questions venture into metaphysics, the branch of philosophy concerning reality's fundamental nature. Singularities aren't just physics problems, but metaphysical puzzles. They challenge assumptions about causation, existence, necessity, law, and explanation. Resolving them physically through quantum gravity would address some philosophical issues, but some philosophical puzzles might remain even with complete physical understanding. The relationship between physics and philosophy at reality's boundaries is complex and mutual. Physics informs philosophy about what's possible. Philosophy helps physics clarify concepts and questions. Singularities exemplify this interplay, demanding both physical and philosophical analysis. The greatest challenge with singularities is that they're fundamentally unobservable, hidden behind horizons or shielded by quantum effects. Black hole singularities are protected by event horizons. Cosmic censorship ensures we cannot see them directly. Light from singularity cannot reach external observers. It's trapped behind horizon. Even if cosmic censorship fails and naked singularity exists, observing it might be impossible. Extreme gravitational lensing and redshift would distort any signals beyond recognition. The Big Bang Singularity occurred before CMB, before any electromagnetic signals could propagate. Observations can only reach back to recombination at 380,000 years. Earlier physics is inaccessible to electromagnetic observations. Gravitational waves potentially probe earlier, perhaps to seconds after Big Bang. But even they cannot directly reveal the singularity at time zero. Quantum gravity effects at Planck Scale leave only indirect signatures. We must infer what happened from consequences encoded in structure we observe today. This makes studying singularities uniquely challenging. We cannot experiment directly. No laboratory can create singularity. Energies and densities required are impossible to achieve. We rely on theoretical reasoning, mathematical consistency, and indirect observational constraints. Hawking radiation from black holes offers potential probe of singularity physics. The radiation spectrum might carry information about interior quantum gravity effects. Deviations from pure thermal spectrum could indicate singularity resolution. But Hawking radiation is extraordinarily weak. Even hypothetical small black holes are barely detectable, and primordial black holes that could be evaporating now might not exist. Gravitational waves from black hole mergers provide another avenue. Ring-down phase as merged hole settles might encode information about interior structure. Precise measurements could test predictions about quantum corrections to black hole geometry. Future detectors might achieve necessary sensitivity. Cosmic microwave background encodes information about early universe physics. Fluctuations pattern depends on conditions at very early times. If Big Bang singularity was resolved by quantum effects, signatures might appear in CMB. Specific features could distinguish between inflation scenarios and alternatives like bouncing cosmologies. Current observations favour standard inflation but haven't definitively ruled out alternatives. Future missions with better precision might detect distinguishing features. Primordial gravitational waves would provide additional constraints. They encode information about inflationary era and potentially earlier physics. Detection would test quantum gravity models and singularity resolution scenarios. Large-scale structure observations also constrain early universe. The cosmic web's statistical properties depend on primordial fluctuations. Precise measurements might reveal features indicating pre-Big Bang physics or quantum gravity effects. Despite these possibilities, observing singularities remains indirect at best. We're limited to inference from consequences, not direct observation. This is fundamental limitation, not just technological. Singularities are hidden by causality structure of space-time itself. We might never observe them directly, even with arbitrarily advanced technology. This creates epistemological challenge. How can we claim to understand what we cannot observe? Science has always dealt with unobservables, atoms, electrons, quarks. We infer their existence and properties from observable effects. Singularities are extreme case of this. Their effects are observable, but they themselves are hidden. This requires trusting theoretical frameworks that extend beyond observational reach. It requires faith in mathematical consistency and physical principles. Some philosophical positions question whether unobservables are real. Instrumentalism treats theories as predictive tools without claiming unobservables exist. Scientific realism maintains theories describe reality, including unobservables. Singularities test these philosophical stances. Are they real or just theoretical constructs? The answer might depend on quantum gravity. If singularities are resolved, perhaps question dissolves. What seemed unobservable might be replaced by something with observable consequences, or perhaps some aspects of reality remain fundamentally beyond observation. Singularities would then mark not just physical limits but epistemological ones, boundaries beyond which knowledge cannot extend, no matter how sophisticated our theories or observations. This is humbling, but perhaps inevitable. Reality might contain aspects we cannot directly access. Understanding singularities means accepting this limitation while pushing knowledge as far as possible. After exploring singularities from many angles, it's valuable to clarify what we know with confidence versus what remains uncertain or speculative. We know with certainty that general relativity predicts singularities under reasonable physical conditions. The singularity theorems, proven rigorously by Penrose and Hawking, demonstrate this mathematically. Given certain assumptions about matter and causality, gravitational collapse inevitably produces singularities. These theorems are mathematical facts within general relativity, not speculative conjectures. We know black holes exist. Observations confirm objects matching black hole descriptions. Stellar mass black holes detected through X-ray binaries and gravitational waves. Supermassive black holes at galaxy centers observed through stellar orbits and accretion disks. Event horizon shadows imaged by Event Horizon Telescope. We know universe had hot dense beginning. Big Bang cosmology is well established. Cosmic microwave background, light element abundances. An expansion all confirm it. The universe was much smaller, hotter, and denser in the past. We know general relativity breaks down at Planck Scale. Quantum effects become important. Classical theory cannot be trusted at such extremes. We know quantum gravity is needed but don't have complete theory yet. String theory, loop quantum gravity, and others are candidates but unconfirmed. These facts are established science, unlikely to be overturned. What remains uncertain is whether singularities truly exist at classical level or are resolved quantum mechanically. Different quantum gravity approaches suggest different resolutions. We don't know what happens at black hole centers, singularity or quantum transition. We don't know what happened at time zero, Big Bang Singularity or bounce or something else. We don't know if information is preserved in black hole evaporation or genuinely destroyed. We don't know if cosmic censorship holds rigorously or has exceptions. We don't know if naked singularities can form or are prevented by quantum effects. We don't know Hawking radiation spectrum precisely, or how evaporation ends. These unknowns are research frontiers, questions driving current work. Some might be answered observationally through gravitational waves, CMB, or black hole studies. Others require theoretical breakthroughs in quantum gravity. What we know provides solid foundation. Singularities are predicted by established theory. Their existence motivates quantum gravity research. They mark boundaries of current understanding. What we don't know keeps the field dynamic. Fundamental questions remain unanswered. This combination of knowledge and uncertainty is a healthy state for science. We're not completely ignorant, but haven't solved all problems. Progress continues gradually. Constrained by observational difficulty and theoretical complexity, understanding what we know helps appreciate progress made. General relativity itself was revolutionary achievement. Singularity theorems deepened understanding. Black hole observations confirmed dramatic predictions. Recognition that quantum gravity is needed marked important realization. Development of string theory and loop quantum gravity represents serious theoretical progress. These accomplishments are substantial even without complete quantum gravity theory. Understanding what we don't know prevents overconfidence and identifies goals. The questions are clear even if answers aren't. Future observations might answer some questions about early universe and black hole properties. Future theoretical developments might resolve singularities mathematically. Eventually, quantum gravity will likely be understood, resolving singularity questions. But timeline is uncertain. Decades or centuries might be required. For now, we work with what we know, constrained by what we don't. Singularities remain mysteries, but well-defined ones with clear paths toward understanding. Singularities capture popular imagination, appearing in science fiction and philosophical discussions, though often misunderstood. The technological singularity, popularized by Ray Kurzweil and others, refers to hypothetical future when artificial intelligence surpasses human intelligence. This is metaphorical use of singularity, meaning point beyond which prediction becomes impossible. It's inspired by gravitational singularities but is a different concept. Technological singularity involves intelligence explosion, recursive self-improvement of AI. Beyond this point, proponents claim society changes so dramatically it's unpredictable. The analogy to gravitational singularities is superficial. Both represent breakdown of prediction. But gravitational singularities are physical extremes where our theories fail. Technological singularity is about complexity and change rate overwhelming predictive capability. Nevertheless, the term's popularity shows how singularities fascinate people. They represent ultimate unknowns, boundaries beyond which everything changes. In science fiction, black hole singularities often serve as plot devices. They're portrayed as wormholes to other universes, time machines, or sources of exotic effects. While creative, these portrayals often contradict physics. Passing through singularity isn't passage to elsewhere but arrival at space-time boundary. You don't emerge somewhere else. You're destroyed by infinite tidal forces, unless quantum gravity resolves singularity differently, making survival possible. Some science fiction explores this. Characters might traverse quantum transitions rather than classical singularities. The film Interstellar dramatized black hole physics, including singularity, with scientific consultation. It portrayed singularity as a place where physical laws break down, allowing unconventional effects, while dramatized. It captured sense that singularities are special, different from ordinary environments. Philosophical discussions often use singularities to explore existence and causation questions. If universe began from singularity, Does this support creation narrative, or does it challenge it by making time itself part of creation? These debates show singularity's relevance beyond physics. They touch fundamental human questions about origins and endings. Singularities also appear in discussions about limits of knowledge and science. Some argue singularities prove science has limits, cannot explain everything. Others see them as challenges to be overcome through better theories. Both perspectives have merit. Singularities do mark current limits, but history suggests apparent limits are often transcended by theoretical advances. Whether singularities represent permanent or temporary limits remains to be seen. Public fascination with singularities likely stems from their extreme nature. Infinite density, time stopping, physics breaking, these are dramatic concepts. They evoke wonder and awe, appropriate responses to natural phenomena at extremes. They also evoke mystery and unknowing, reminding us how much we don't understand. This combination makes singularities compelling topics for popular science communication. Explaining them accurately while maintaining sense of wonder is a challenge. Oversimplification risks misunderstanding. Too much technical detail loses audience. The balance involves conveying both what we know and what remains mysterious. Singularities are real predictions of established theory. Not mere speculation, but they're also open questions where current understanding reaches its boundary. This duality of being both known and unknown makes them fascinating. They're concrete enough to study rigorously, yet mysterious enough to inspire continued exploration. For general audiences, singularities offer a window into frontiers of physics. They show how science operates at its boundaries, pushing into unknown with mathematics and observation. They demonstrate intellectual humility, acknowledging when theories reach their limits, and they promise future discoveries. When quantum gravity is understood, singularities will be explained. That future understanding will likely be as revolutionary as general relativity itself. Public interest in singularities helps support research, both intellectually and financially. Curious audiences motivate scientists and justify funding for fundamental research. So while popular imagination sometimes distorts technical details, overall fascination is positive. It connects human curiosity to scientific exploration, linking everyone to quest for understanding reality's extremes. Understanding singularities requires appreciating mathematics involved, how equations signal their own failure. General relativity describes space-time geometry using differential geometry. The metric tensor encodes distances and angles. Curvature tensors describe how space curves. Einstein's field equations relate curvature to matter and energy distribution. These are 10 coupled nonlinear partial differential equations, extraordinarily complex. Solving them exactly as possible only for highly symmetric situations. Schwarzschild solution assumes spherical symmetry and no rotation. Kerr solution adds rotation. These exact solutions contain singularities at their centres. Mathematically, singularities appear where geometric quantities diverge to infinity. The Riemann curvature tensor measures space-time curvature. Components become infinite at singularities. Scalar curvature invariants, quantities independent of coordinate choice, also diverge. The Kretschmann scalar, formed from Riemann tensor, becomes infinite at true curvature singularities. This mathematical divergence signals physical breakdown. Theory predicts its own invalidity. Coordinate singularities, by contrast, are artifacts of coordinate choice. Event horizon in Schwarzschild coordinates appears singular mathematically, but switching to Eddington, Finkelstein or Kruskal coordinates shows it smooth. Curvature invariants remain finite at horizon, confirming its coordinate singularity. Distinguishing coordinate from curvature singularities requires mathematical sophistication. Must check whether infinity persists in all coordinate systems. Only coordinate-independent quantities like curvature invariants reveal true singularities. The singularity theorems use global methods, studying spacetime's overall causal structure. They don't solve field equations directly, but prove that under certain conditions, singularities must occur. The proofs use techniques from differential geometry and topology. They analyse geodesics, paths that free-falling observers follow, incomplete geodesics, paths that can't be extended further, indicate singularities or boundaries. The theorems show that under reasonable conditions, incomplete geodesics are inevitable. This mathematical result has profound physical implications. It means general relativity generically predicts its own breakdown. The mathematics alerts us to where new physics is needed. Quantum gravity must be formulated mathematically to resolve singularities. String theory uses advanced mathematics, topology, algebraic geometry, conformal field theory. Loop quantum gravity employs functional analysis, representation theory, and knot theory. Both require sophisticated mathematics beyond classical differential geometry. The mathematical complexity reflects physical depth. Reality at these extremes is mathematically rich. Understanding singularities mathematically helps physical intuition. We see not just that theory breaks, but how and why. The specific way curvature diverges tells us about singularity's nature. For instance, Schwarzschild's singularity is different from Big Bang singularity mathematically. One is point in space, other is moment in time. Mathematics captures this distinction. Mathematical tools from analysis help classify singularities. We distinguish essential singularities, poles, and removable singularities. These classifications from complex analysis inform singularity studies in general relativity. The mathematics also guides resolution attempts. Knowing how classical theory breaks suggests what quantum theory must provide. If curvature diverges in a particular way, quantum corrections must counteract that specific divergence. Mathematics is thus both diagnostic and prescriptive. It diagnoses where theory fails and prescribes what fixes must accomplish. For students and researchers, mathematical rigour is essential. Vague physical intuitions can mislead. Mathematics keeps reasoning precise, but mathematics alone isn't enough. Physical interpretation gives mathematics meaning. The interplay between mathematical formalism and physical intuition is where progress occurs. Singularities exemplify this interplay. They're mathematical features with physical significance. Understanding them requires both mathematical precision and physical insight. Looking forward, what prospects exist for understanding singularities, for resolving these breakdown points of physics? Observationally, several developments promise progress. Gravitational wave astronomy is rapidly advancing. LIGO, Virgo, and Cagra detect mergers regularly. Future detectors like Einstein Telescope and Cosmic Explorer will be far more sensitive. They might detect signatures of quantum gravity in extreme conditions. Black hole ringdown encodes information about space-time near horizon. Deviations from general relativity predictions could indicate quantum corrections. Testing these requires precision beyond current capability, but within future reach. Space-based LISA will detect lower frequency gravitational waves. Accessing different sources, it might observe extreme mass ratio inspirals. Small objects spiraling into supermassive black holes. These provide precision tests of strong field gravity near horizons. Cosmic microwave background observations continue improving. Future missions might detect primordial gravitational waves through B-mode polarization. This would constrain inflation models and potentially probe Planck Scale physics. Signatures of pre-Big Bang cosmologies might be distinguishable from standard inflation. Loop quantum cosmology and bouncing scenarios make specific predictions. Improved observations could confirm or rule out these alternatives. Theoretically, progress in quantum gravity continues. String theory calculations become increasingly sophisticated. Understanding holography and gauge gravity duality deepens. These developments might reveal how string theory resolves singularities. Loop quantum gravity refines calculations of bounce scenarios. Numerical simulations improve, testing full quantum dynamics. Other approaches, like causal dynamical triangulations and asymptotic safety, advance. Diverse theoretical efforts increase chances of breakthrough. Interdisciplinary connections grow stronger. Quantum information theory informs black hole studies. Condensed matter systems provide analogues for gravitational phenomena. These cross-pollination suggest new approaches to old problems. Computational physics enables new explorations. Numerical relativity simulates black hole mergers with increasing accuracy. Quantum cosmology calculations become feasible with better computers. This allows testing theoretical ideas that were previously intractable. Education and communication improve public understanding. More people learn about singularities through accessible explanations. This broader interest supports research and attracts talented students to field. The challenges remain formidable. Singularities are extraordinarily difficult problems. Resolving them requires unifying quantum mechanics and general relativity. This is one of physics' hardest problems. Unsolved for nearly a century. But progress is real. Understanding deepens incrementally. Each observation constrains possibilities. Each theoretical development clarifies issues. The path forward involves patient systematic work across multiple fronts. No single observation or calculation will suddenly resolve everything. Instead, accumulation of evidence and refinement of theory gradually converges toward answers. The timeline is uncertain. Breakthroughs might come soon or require decades. History suggests fundamental problems take time. Quantum mechanics took 30 years from initial ideas to mature theory. General relativity took Einstein 10 years of intense effort. Quantum gravity might take similar or longer timescales. But eventual success seems probable. The questions are well posed. We know what needs explaining. We have frameworks to develop. Observations provide constraints. Mathematics guides reasoning. These are ingredients for scientific progress. Whether singularities are resolved, revealed to be artifacts, or understood in entirely new ways remains to be seen. But understanding will come eventually through persistent effort. The future of singularity physics is bright, full of possibility for discovery. Those working on these problems are pushing knowledge to its frontier. Their efforts will eventually bear fruit, revealing whether the universe truly breaks or merely transitions at these extreme points. As we conclude our exploration, perhaps the most important insight is learning to embrace singularities as profound mysteries that might never be fully resolved. Science often provides complete understanding. Many phenomena are well explained, but some questions remain stubbornly mysterious despite centuries of effort. Singularities might be such questions resisting easy resolution. This doesn't mean we should stop trying. Effort is worthwhile even without certain success, but it means accepting that complete understanding might elude us. There's value in mystery itself. Not everything needs to be explained away. Singularities remind us that reality exceeds our current understanding. They're humbling, showing limits of human knowledge despite impressive achievements. This humility is healthy. It prevents arrogance and keeps us intellectually honest. Singularities also inspire wonder. They're genuinely extraordinary phenomena, points where physics breaks, where infinities arise, where space-time ends. These are remarkable features of the universe we inhabit. Appreciating their strangeness enhances sense of living in mysterious cosmos. The unknown has always driven science. Curiosity about what we don't understand motivates research. Singularities are frontiers precisely because they're not understood. They're opportunities for discovery, chances to expand knowledge. Whether we succeed or not, the pursuit itself has value. It develops new mathematics, refines observations, trains scientists. It pushes technology forward through requirements for better instruments. It connects to broader questions about existence, time, causation. All these benefits accrue regardless of whether singularities are ultimately resolved. for individuals. Contemplating singularities offers perspective. Our everyday concerns occur in a universe containing such extremes. This context can be comforting or unsettling depending on temperament. Comforting because our problems seem small against cosmic backdrop. Unsettling because universe is stranger and more extreme than ordinary experience suggests. Both responses are valid. Singularities evoke strong reactions because they're genuinely profound. Philosophically, singularities teach acceptance of limits. Not everything can be known. Not every question has answer. Some aspects of reality might be inherently mysterious. Accepting this doesn't mean giving up, but recognizing boundaries. We can understand vast amounts while acknowledging some things remain beyond reach. This mature perspective balances confidence in scientific method with humility about its scope. Scientifically, singularities exemplify how theories reveal their own incompleteness. General relativity predicts singularities, then breaks down at them. This self-awareness is remarkable. The theory tells us where it fails. This guides development of better theories that hopefully don't fail the same way. Or perhaps they fail differently, revealing new boundaries to cross. Science progresses by pushing against limits, finding where theories break, developing better theories. Singularities are where this process operates most dramatically. They're extreme test cases revealing what physics can and cannot currently explain. For future generations, singularities will be historical curiosity or current problem, depending on progress. Maybe quantum gravity will be understood by then, singularities explained. Or maybe they'll remain mysterious, perpetually just beyond complete understanding. Either way, the journey of exploration is what matters. The questions asked, methods developed, insights gained along the way. These constitute scientific progress regardless of final answers. As we drift toward rest tonight, singularities can be contemplated peacefully. They're distant from our everyday experience. They don't threaten us. They're intellectual puzzles, extreme conditions revealing physics limits. Understanding them better would be wonderful achievement, but not understanding them completely is acceptable too. They're mysteries worth pondering, boundaries worth exploring. They show that universe is deeper, stranger, and more wonderful than we might otherwise imagine. Living with mystery, pursuing understanding while accepting limits, is human condition at its best. Singularities embody this beautifully, being both extremely well-defined mathematically and profoundly mysterious physically. They're where universe breaks, where our knowledge ends, where wonder begins. Thank you for journeying with me through singularities, these profound breakdown points where physics reaches its limits and reality becomes undefined. I hope you found peace in understanding that some boundaries cannot be crossed, that infinities mark not failures but frontiers, and that mysteries like singularities enrich rather than diminish our appreciation of the cosmos. Singularities exist at black holes' hearts and marked our universe's beginning, points where density becomes infinite, where time stops. Where general relativity breaks down and quantum gravity must emerge. We've explored their mathematical inevitability through singularity theorems, their protection by cosmic censorship, their connection to information paradoxes and quantum effects. String theory suggests they're replaced by extended objects. Loop quantum gravity predicts bounces, but the truth awaits quantum gravity's completion. Wherever you are now, I hope you're ready for deep rest. Your breathing has found its gentle rhythm. Your mind has released the need for complete answers to impossible questions. The singularities we've explored perhaps help you feel both small before cosmic extremes and significant in your capacity to contemplate breakdown points of reality itself. Sleep well tonight, knowing that singularities hide within every black hole yet remain forever beyond our direct observation, that they marked time's beginning yet might not truly exist quantum mechanically, that they represent both physical extremes and theoretical boundaries where new discoveries await. Dream peacefully of infinite densities resolved by quantum effects, of big bounces replacing big bangs, of information preserved through subtle correlations, of Planck Scale physics revealing what classical theory cannot describe. Dream of event horizons shielding singularities from view, of tidal forces stretching space and time, of Hawking radiation carrying away black holes atom by atom. Dream of mathematics signalling its own breakdown, of theories predicting their incompleteness, of scientists working patiently toward quantum gravity. Dream of mysteries that inspire rather than frustrate, of boundaries that define rather than limit, of unknowns that enchant rather than threaten. Good night. May your sleep be undisturbed and restorative. May tomorrow find you refreshed and renewed. And may you carry forward an appreciation for breakdown points that reveal reality's depth, for mysteries that drive understanding forward, and for limits that show how far knowledge extends while hinting at what lies beyond. Where does the universe break? At singularities, points of infinite density where space-time's smooth geometry dissolves, where general relativity predicts its own failure, where quantum gravity must replace classical description. Black holes harbour them at their centres, crushed to zero volume behind event horizons. The Big Bang was one, marking time's beginning or perhaps a quantum bounce. They're where mathematics produces infinities, where physical laws cease to apply, where our theories admit incompleteness. Yet singularities might not truly exist. They might be artifacts of classical approximation, resolved by quantum effects we don't yet understand. String theory smooths them with extended objects. Loop quantum gravity bounces through them with quantum repulsion. Perhaps Planck Scale physics replaces infinities with extreme but finite conditions. Perhaps space-time itself becomes discrete or dissolves into quantum foam. Perhaps singularities are illusions that disappear in complete theory. But illusion or reality, they serve crucial purpose. They mark boundaries between known and unknown, between classical and quantum gravity regimes, between what we understand and what awaits discovery. They're signposts pointing toward new physics, motivations for developing quantum gravity, tests for any theory claiming completeness. Where universe breaks is where science must grow. We live in a universe containing these breakdown points, embedded in space-time that curves toward infinities we cannot observe. Dark matter holds galaxies together as we explored before. Singularities mark where holding together fails, where gravitational collapse overwhelms all resistance. Where infinity beckons, both invisible phenomena, dark matter and singularities, shape cosmic architecture in complementary ways. One builds structure, the other marks structure's ultimate limits. Understanding singularities means accepting that physics has boundaries, that not everything is explainable with current knowledge, that theories sometimes predict their own incompleteness. This intellectual humility is strength, not weakness. It drives progress, motivates research, keeps science honest about its scope and limits. We know vast amounts. We acknowledge what remains unknown. Both truths coexist without contradiction. The singularities hide in black holes throughout cosmos, billions of them, each containing breakdown point where classical physics fails. They marked our universe's beginning, the Big Bang from which everything emerged or through which everything bounced. They connect to deepest questions. Why does anything exist? How did time begin? What happens when matter is compressed to infinite density? Does information survive? Is determinism preserved? Can we observe the unobservable? These questions might never be fully answered. Some mysteries persist despite centuries of effort. Singularities might be such mysteries, forever just beyond complete understanding. This possibility should neither discourage inquiry nor diminish wonder. The journey matters as much as destination. The questions themselves are valuable even without certain answers. The pursuit develops knowledge, refines methods, inspires generations of scientists working at reality's frontiers. For you, tonight's listener, singularities are distant abstractions, extreme conditions far removed from everyday experience. Yet they're part of universe you inhabit, features of reality as real as stars or planets, despite being hidden and incompletely understood. Contemplating them connects you to cosmos at its most extreme, to physics at its boundaries, to human knowledge at its frontier. This connection enriches perspective even as sleep approaches. The universe breaks at singularities. Physics breaks, our understanding breaks, time itself might break. But these breakdowns aren't failures of nature. Nature knows what it's doing. They're failures of our descriptions, boundaries of our theories, invitations to develop better frameworks. General relativity was revolutionary advance, explaining gravity as space-time curvature. Its prediction of singularities revealed its own limits, pointed toward quantum gravity. When quantum gravity is understood, new boundaries will likely appear, new breakdowns discovered. New mysteries to explore. Science advances by finding where theories fail and building better ones. Singularities are beautiful in their extremity, profound in their mystery, important in their implications. They're where space-time ends, where physics reaches beyond itself, where human understanding confronts its limits. They're worth pondering as consciousness fades towards sleep, worth dreaming about in abstract mathematical terms, worth carrying as reminder that universe contains depths we've barely begun to fathom. Where does universe break? Everywhere quantum gravity is needed. At Planck Scale, in black holes' hearts, at Big Bang's origin. In these places and perhaps others we haven't discovered, the breaks mark boundaries, edges, frontiers. They show how far we've come and how far we have yet to go. They're challenges and opportunities, problems and promises, endings and beginnings. Sleep now knowing that mysteries remain, that universe exceeds understanding, that some questions await answers while others might persist forever. Rest peacefully with the breakdown points, the infinities, the singularities where physics fails and wonder begins. Dream of quantum gravity resolving what classical theory cannot, of bounces replacing bangs, of extended strings smoothing infinite points, of Planck Scale foam replacing smooth geometry. Dream of scientists' future who will understand what we cannot, of observations revealing signatures from breakdown points, of mathematics capturing what words fail to express. The universe breaks where it must, revealing where new physics is needed. And we explore these breaks with patience, rigour, imagination and humility, acknowledging both what we know and what remains gloriously, profoundly, beautifully unknown. Good night.